this video we're going to study LC oscillators, which we can also analyze using loop gains. Like phase shift oscillators, these circuits implement feedback around linear amplifiers to create oscillators. However, using second-order feedback networks with both inductors and capacitors lets you make much more compact oscillators, which we'll see soon. We're going to start analyzing this by looking at some interesting LC networks. The network pictured on this slide is called a tapped capacitor network. The input impedance of this network is given by the parallel combination of the inductor impedance and the two series capacitor impedances. Because we're assuming there's no resistance in this network, we get a funny looking second order system for this impedance. If you substituted j omega into the denominator, you'd find that it's always real. Right, this j omega squared turns into just minus omega squared. So that means that the overall impedance is always imaginary, because you'll get a j omega L on top. You'd also find that the phase shifts from positive to negative abruptly at omega equals 1 over square root of LCF, which is when the sign of this denominator changes from positive to negative. So these funny behaviors are because we haven't included any resistors in our circuit, which means that this is kind of an idealized system that will transfer infinitely quickly in response to frequency changes. So those behaviors are distracting, but they paint the broad strokes of how a parallel LC resonator works. At low frequencies it looks purely inductive, because the caps are high impedance, and so we get a overall positive and purely imaginary impedance, j omega L on top. At high frequencies it looks purely capacitive, so it has a purely imaginary and negative impedance. This LCF s squared is bigger than 1, so you have a negative value on the bottom here, and an overall negative imaginary impedance. And because the phase shifts right at 1 over square root of LCF, the resonant frequency, you wind up with a purely real impedance at exactly that frequency. So our impedance is purely real at resonance. And that means that our voltage and our current are only in phase at resonance. The voltage and current either lead or lag one another outside of that. There's also a gain in this network between V in and V out. The ratio is given by a capacitive divider. And remember that capacitive dividers have C1 on the top when you care about the voltage on C2, as seen here. There's a natural dual of these tapped capacitor networks called tapped inductor networks. These are particularly easy to build because you can just grab some wires in the middle of a wound inductor to make the V out port. So both of these networks seem interesting in feedback because they have this phase crossing behavior, where there's one frequency where they have exactly 0 phase. And they also have a tunable gain built into them. So maybe we can make them into oscillators. So there are a lot of oscillators that use resonators in feedback, and we don't have time to analyze all of them. We're going to look at the Colpitts oscillator in the common base configuration, which uses a tapped capacitor network and appears up here in the left. As the name of the circuit suggests, there are other variants of Colpitts oscillators, most notably the emitter-follower configuration, which is the kind of oscillator that students accidentally build in the lab most often. There are also other kinds of oscillators, like Hartley oscillators, which use tapped inductor feedback network, clap oscillators, which add a few more tuning capacitors to their resonator, and Pierce oscillators, which are often used with quartz crystal resonators. All of them work on similar principles to this Colpitts oscillator. If you understand one, you can figure out the rest. We can make a small signal model for this oscillator, and we see that the inductor going to the power supply winds up connected to small signal ground, and that makes it much more obvious that these three components form a tapped capacitor network. We also open-circuited R big and short-circuited C big. And we could pick values of R big and C big to make that simplification reasonably accurate. Later in the analysis we'll be assuming that RO is much bigger than 1 over j omega C1, and R pi is much bigger than 1 over j omega C2. which looks like the circuit kind of just looks like a GM generator driving this tapped network. We can describe this circuit using a block diagram. If we decrease VE, that makes VBE more negative, which makes IC smaller. If IC gets smaller, then that results in VC going up because pulling current up through the resonator network drops our voltage. And VC is related to VE just by this capacitor divider. VC drives VE through this cap divider. So we can write a feedback loop through all of these components. We can write our loop gain using the Z-in of the resonator we found on the last page and multiplying all of these blocks together. And we're hoping this L of j omega is equal to 1 because this feedback loop is in net positive feedback. There's no negative sign on this summing junction. The expression only has 0 degrees of phase exactly at the resonant frequency, so the oscillation frequency is 1 over the square root of LCF. In order to have our magnitude be equal to 1 at that frequency, we need to sub omega osc into this, j omega osc into this expression. However, that's tough because it results in the denominator of this idealized impedance going to 0. So we'll just add a little bit of parasitic resistance to our inductor, which would be left behind in this denominator. And that leads us to this expression, where we find that our gain is 1 if 1 over GM is equal to, is canceling out this capacitive divider, and then this funny ratio between the square root of L over CF and 1 over R series. This funny ratio is actually a really interesting number. L over CF is called the characteristic impedance of the resonator, and R series is sort of a parasitic resistance. The ratio of the two is called the quality factor, and it tells you how good a resonator is at storing energy, which, as you might imagine, is quite important when you're designing oscillators. But at any rate, you can tune your capacitive divider network and your bias point in order to make this equality true. So this control theory analysis answers the questions we care about. We know the frequency of oscillation, and we know how much gain we need in order to make our oscillation stable. However, there's another way to come to this result that's rooted in circuit analysis, and it's worth seeing so that you understand it when you see it in other references. So this circuit analysis technique focuses on the Thevenin impedance seen by the inductor. The oscillation condition for circuit analysis is that the inductor sees a negative real impedance. And specifically, the real impedance that it sees has to be negative enough to cancel out its parasitic resistance. But in this case, we're saying there's no parasitic resistance, so if the impedance is negative at all, the circuit will oscillate. And so the general idea there is just that if an inductor and a capacitor that are hooked together with 0 resistance will oscillate forever. And so this GM generator is canceling out the effect of any real resistance that's in the inductor or your capacitor network. To make our life easier, we're going to assume that most of our current is flowing in the cap network. So R pi is bigger than 1 over j omega c2, and RO is bigger than 1 over j omega c1, which is a reasonable assumption if the frequency of oscillation is pretty high, and it generally is. Okay, so if we do that though, we can open circuit this and open circuit this, and we realize that the impedance we're looking into just looks like a left-right network. C1 is in parallel with GM, C2 connects from GM to ground, and has VBE across it. So we can calculate the input impedance very quickly. as 1 over C1s plus 1 over C2s plus GM over C1 C2s squared. And if we substitute in j omega, then this term becomes negative and real. So it's minus GM over C1 C2 omega squared. So that means we have a negative real part to our Thevenin impedance, and this thing will oscillate. Now again, if you include some resistance in your analysis, then this term needs to be more negative than the real parts of other expressions. And that winds up being the same as the gain criterion we have over here. You can also use this analysis to find omega osc, because at your oscillation frequency, your inductance and capacitance have to resonate, meaning their imaginary parts exactly cancel out. So your inductor is just in parallel with whatever the imaginary part of ZTH is here, and so when the parallel combination of those is 0, you're at your oscillation frequency. As a final note, I want to emphasize how easy these oscillators are to make by accident. For instance, I've seen Colpitts oscillators where C2 is a bypass cap, like a CE, in order to build an amplifier, and C1 is a breadboard parasitic, and this inductor is just a long wire to the power supply. So watch out, use careful circuit construction techniques to avoid making these. So in summary, tapped LC resonators let us build oscillators because they provide attenuation and in-phase voltage and current at resonance. The Colpitts oscillator oscillates at a frequency of omega osc equals 1 over the square root of LCF. You can analyze LC oscillators with either control theory or circuit analysis. And it's very easy to make an LC oscillator by accident.